the explosion and let's say the fire issues is not one separate bottlenecks inside the mill, because now let's change a little topic. We are still in the mill, but we consider the mill performance. You can see the plenty of the columns, but it can be explained in a simplified way. We consider the first parameters is the flue gas temperature. The blue one is the opening of the cold air flap, so it can be open in 100% or it can be closed, is 0% of the opening. And also we consider the opening of the hot air flap. In the overall meaning, if we consider that the totally let's say opening of the air flaps, we can say that here you can we have different cases, but this is the coal. This is the co-combustion with such coal with different biomass in the same level of the share. It is 15%. So as I said, if we consider the overall the total air flap opening, so we notice that in case of biomass co-firing, we have to open more the cold air flap due to the safety issues, because as you already know that the biomass explosion probability is higher comparing to the coal. So we have to open more cold air flaps due to some safety issues. We have to avoid increase the temperature inside the mill. But also the another point is we have to increase the total airflow rate. Why? Because if we mill the biomass, especially the raw biomass, so the bigger particles of the biomass can still exist inside the mill. So in fact, we have to increase a little the air velocity to remove such bigger particles from the mill. So we have to increase a little the total airflow rate. Another bottleneck related with the mill performance is the increasing of the energy demand, because the biomass, as you know, is have a fiber-like structure. So if we want to mill the biomass, we have to put more energy. And let me show you some numbers and comparisons between the particle size distribution and the energy demand. Now you can see the table. Here is the biomass share. So 0 means that we mill only the coal. And here it is the biomass share, in fact, is not very high. It's 6%. But you can see that if we increase the biomass share, if we introduce the biomass, we have more bigger particles. So R 0.1, so that's mean it is the percent of the of the particles below 100 micrometers and below 200 micrometers. So in fact, the conclusion is that if we introduce the biomass inside into the mill, we increase the number of the bigger particles in the, let's say, fuel, pulverized fuel. But what about the energy demand? This is the comparison between the energy demand of a coal, the raw biomass, and the torrefied biomass. You can see the energy, the energy necessary for grinding for a typical coal is between 7 to 36 kilowatt-hour per ton. For raw biomass is even 100 times more. For torrefied biomass, of course, it is less, but we still need more energy. But if we consider the co-milling of the biomass with the coal, so you can see the baseline for coal in such experiments taken from the literature is between 30 to 65. If we mix the coal with the torrefied biomass, it depends on the torrefaction temperature. If the torrefaction temperature is quite low, so the energy demand for milling is higher. In my opinion, the very interesting is here comparison of the biomass, comparison of the energy demand when the steam explosion biomass treated is introduced with the torrefied biomass. So you can see that energy demand is much lower comparing to this previous baseline of the lower temperature of the torrefaction. For your imagination, the grinding energy demand for coal is much more lower if we compare it with the raw biomass. Of course, it is still possible. The milling of the raw biomass is possible. Even we can change the mill, the type of the mill. Nevertheless, the energy demand for the raw biomass milling is much more higher comparing to the coal milling. So we identify as a serious bottleneck. Now we let's say move from the milling into the boiler and into the boiler parameters and try to identify the bottlenecks in the boiler. Of course, the very important is to underscore one of the very crucial bottleneck is related with the ash-related issues, because as you know, the paddy straw, the composition of paddy straw, especially the chloride content and the sodium potassium content is high, so the probability of the slugging falling is very high. But not only we can identify also another bottleneck. That's mean the parameters of steam. If we consider the parameters of leaf steam and the reheated steam, you can see the violet and the orange one, and the water injection to the leaf steam and the water in the injection for the reheated steam. You can see here, as the previous time, the different cases. First is the baseline when the only coal is applied, and the second and third and next is the co-firing of this coal and with the biomass at the specific one share. That means is 15%, and this number represents the capacity of boilers is the tons of the steam per hour. So from the lower to higher capacity. So you can see here, this red line is very important. It is the, let's say, our aim. We need to obtain such a steam parameter, the steam temperature. In such case is 535 degrees of Celsius. So you can see, in case of coal, we can obtain such parameter. Of course, we can control it by injection of the water into the leaf steam or even to the reheated steam. But in case of the biomass co-firing, in some cases we cannot obtain the steam temperature to the certain level, to the level of 535 degrees of Celsius. And we rather not use the water injection to the reheated steam. So we have the avoided control. We cannot control the steam temperature inside the boiler. So sometimes in engineering jargon, we call it the slide of the boiler. We cannot full control of the steam parameters. Of course, the steam parameters means the efficiency of the boiler and efficiency of the producing